In this video, we're going to look at two types of growth, linear growth and exponential growth. So linear growth is growth with a constant rate of change. We kind of saw this before. We talked about this when we talked about proportional. So for instance, we have a graph of a job where you're paid hourly, and that means that your pay is going to go up linearly because you're going to be making a certain amount every hour you work. So in this graph, they want to know what the hourly rate is. Okay, so when I kind of first look at it, I notice that at 10 hours, it's above 100, which isn't as useful to me. At 20 hours, it maybe looks like it's halfway, maybe 250. I do notice though right here, it kind of looks like halfway at 25 hours, we hit $300 in pay. Okay, so if I go ahead and grab my calculator and do 300 divided by 25, I get 12. So I'm thinking it's $12 per hour. Here, I'm going to kind of write it shorthand like that. So at 20 hours, then that would be about 240, which kind of makes sense. It's pretty close to halfway. All right. 10 hours, 120. That actually looks like it kind of seems reasonable, and so forth. Okay. So an adult of average size burns 112 calories for every mile they run. The relationship is linear. Every mile corresponds to 112 calories. If you want to burn 1,120 calories by running, you would need to run how many miles? Well, I notice that if this is 112 calories and there you're wanting to burn 1,120 calories, that's 10 times as much. If I multiply 112 by 10, that gives me 1,120. So that means then that 10 miles is what I would need to run. Or I could just take 112 and keep adding 112 to it until I get to 1120. Or I could divide 1120 by 112, and that's going to give me 10. So I'm like, 10 miles is what's going to take to make that. Okay, so exponential growth is multiplying by the previous output. So that's how exponential growth works. It's this constant percent of increase. We're increasing by a percent over and over and over again. So linear, you're adding; exponential, you're multiplying. That's the big sum up. So let's look at this example. Let's say we have cells that are dividing into two cells, and here's what it kind of looks like. So it's difficult to count the number of cells in day 4, but based on the pattern, how many cells must there be in day 4? Okay, so for day 1, we're starting with 1 cell. Day 2, there's 2 cells. Day 3, day 0 is 1 cell. Day 1, there's 2. Day 2, there's 4. Day 3 is, let's see, 1, 2, 3, 4, 5, 6, 7, 8. 8 cells. And hey, that makes sense because it's dividing into 2 cells every time. So if we keep this pattern up, it's going to double, right? There's going to be 16 cells here. So 16 in day 4. So day 5, we'd be doubling again, which would be 32 cells. So we're doubling every time. That is the pattern. So if it was linear, meaning we were adding to every time, okay, that's how that growth would look like. So is this growth linear? No, it's not adding to every time. No, it's multiplying, not adding. So let's actually fill it in based on what it's really behaving. So day 1, it was 2. Day 2, it was 4, 8, 16. We got 32. So then the next one would be 64. I'm doubling 32. Okay. So the size for each jump, go ahead and refill this out, 16, 64. So from here to here, it jumped by 2. From here to here, it jumped by 4, and then by 8, and then by 16, and then by 32. So we're adding to itself every time, right? These two numbers are matching every time because we're adding it to itself, okay? That's not linear growth, that's exponential growth. So how would you describe the growth from one day to the next? A better way of doing that is to talk about multiplying, not adding. So let me fill these back in. And instead we are timesing by 2 every single time. That's the consistent thing, multiplying by 2. A quantity that is growing exponentially may grow slowly at first, but then starts to get fast. So this is what the graph of that looks like. Visually, it's growing very rapidly. So how many cells would there be on day 10? Okay, so we know how many cells were on day 6. There was 64. So that means I'd be multiplying by 2 for day 7, 8, 9, 10. Or in other words, I'd be multiplying by 2 4 more times because that's representing 4 more days. So if you were to do that, you'll end up with 1,024. So how long to 1,000,000 cells? Well, that's going to take a while. But really, we're trying to figure out how many times we have to keep multiplying by 2 before we're going to see 1,000,000. Now, you could take 1,000,000 and just start dividing it by 2 and kind of approximating how many times you can do that. That's one way to do it. So if you grab your calculator and divide by 1,000,000, divide 1,000,000 by 2 and see what you come up with. Now, if you do that, if you grab it and start dividing by 2, what you're going to see is that eventually you're going to hit some decimals. And though you could keep dividing, it's going to be kind of tough to keep track of. It might actually be easier to work with the number we already have. In other words, take 1024 and keep timesing it by 2 until you hit over 1,000,000. All right, so try that instead. So grab your calculator, take 124, times it by 2, and see how many times you have to do that until you get to 1,000,000. I'm going to pause here for a second, or just pause the video. Okay, so here's how many times you would probably have to do that. 10 times. So if you multiply by 2 10 times, you should finally hit 1,485,076. I said that wrong. 1,048,576. There we go. Now I said it right. So it basically you'd have to multiply by 2 for 10 days, like 10 more times, right? Okay, I'm not going to write all the 2s that would take. But really that means that's 20 days total, because 1024 was 10 days. And in order to get to 1,000,000, it had to go for 20 days. And in 20 days, by the way, you hit 1,048,576. Just going to write the number that I got on the calculator. And hopefully you got 2 after you multiplied it by 2 10 times. All right. So can this kind of growth continue indefinitely? Well, in terms of cells, no. Right? Especially if the cells run out of space or reach some sort of moment where maybe they're attacked, right? Or the temperature changes and their, climate changes. So no, it can't continue indefinitely. No. The environment. Wow, I can spell. Environment will eventually limit them. Most likely, they'll run out of space. Like, oops. Running out of space. Or like I said, maybe the temperature changes. Because sometimes they don't thrive in certain temperatures. Or maybe something negative is introduced to the cell group that attacks the cells, right? There's like lots of reasons why they may not continue growing like that. Okay, so Eugene's population was about 169,000 in 2017. Now the growth rate isn't always the same, but let's just assume for the approximately that it's growing by a rate of about 2% each year. So let's find 2% of 169. So to do that, I'm going to take 0.02 and I'm going to times it by 169,000. And I get 3,380. So that's how much it's going to grow by. That's how many people are going to be in the population. So in 2018, then I need to add that 3,300 basically. I need to add to this amount, the 169, that number, 169,000. So when I add it, I get 172,380. So 172,380 people. Okay, so if it goes again, sorry, part C. Can you multiply 169 by 1.02 to find the next population? So let's do that. Let's take 169,000 times it by 1.02. And yep, we get the same number. So here's what 1.02 represents as a percent. As a percent, it's 102%. So what they're doing is they're taking the 2% annual increase and they're adding it to 100%. So they're increasing the population by exactly what it normally is, which is 100% plus that extra 2%. So if I times this by 1.02 from here to here, we should be able to figure out how much the population is going to grow each year. All right. So grab your calculator and let's get to multiplying. So this one I get 175, 8. Let's say 28. We'll round up to a whole person. Okay, so 175,828. So I rounded that 0.6. I got 7.6. I rounded the 7 up to 8. So that makes more sense when we're talking about people. Okay, so I'm going to times that by 1.02, and I'm just using the decimal, by the way. I times the decimal in my calculator by 1.02, and I'm getting now 179,344, rounding to the nearest number. Probably could round up now that I'm thinking about it, because a whole person doesn't make sense to have a point decimal of a whole person, right? You know what? I'm going to round up. Makes more sense. All right. So now I'm going to take that number and just multiply it by 1.02 again. And I am getting 182,931. Okay. And again, there's a decimal, so I should round it up to 32. Because again, we're talking about people. So take a decimal, even a 0.1 is going to count as like a whole person. So I'm just constantly rounding up. I hope you guys are kind of seeing that and following along with that on your calculator. Okay, so timesing by 1.02 again. I'm getting 186,590. Okay, now if you aren't using the original decimal, if you're not just taking that number in the calculator and timesing it by 1.02, your answer is about to diverge from mine. You're going to actually be rounding to 91. It's okay. If you round it up to 91, it's not a big deal. But I'm just taking the number in the calculator and I'm multiplying by 1.02. That's what I'm doing. But if you're taking each of these whole numbers right here that I've written down and multiplying by 1.02, like re-entering the number and multiplying by 1.02 every time, then yeah, you're going to get 186591 for the last one. Okay, just to be aware. It's okay that we're different. Don't stress about that. Just kind of depends on the rounding and no big deal. All right. 1% difference is not enough to get upset. I'm trying to erase all the highlighters. Sorry. Let me fix that. I think that was an 8. All right. So, and how many years will their population exceed 200,000? Well, we're getting close, right? But it is not going, it's going to take a little while before we're going to hit 100,000. I mean, 200,000. So it might be useful to take away the 169,000 that we started with, which comes out to 31,000. And then take 31,000 and divide it by 1.02. I'm getting did I do that right? Doesn't seem like it because I'm getting 30,392. Yeah, that doesn't make sense. So I don't think that method's going to work. I was hoping to find a shortcut, but I don't think I'll be able to. That's okay. So basically what I'm going to do is I'm going to keep multiplying by 102, 1.02. I'm going to keep multiplying in my calculator by 1.02 and figure out how many more times do I need to multiply this number by 1.02 in order to get to or exceed 200,000. So if you want to pause your video and work on that, and then I will go ahead and tell you what I got to do that. So for me, it looks like it would be, I'd have to do it another 4 times. So that would be 8 times total because I already did it 1, 2, 3, 4 times, and I have to do it another 4 times. So 8 years. In 8 years, it will exceed 200,000. Sorry, tried to shortcut it, but it did not work. That backfired on me. I know why, but yeah, you're just going to have to kind of do the math to work that out.